Alright, this is going to be a whole issue, I'm going to be honest with you. What I'm going to do is, I'm going to try and just do the volume, because he did do the volume, he gave it to you as pi squared over 2. And that means he just integrated that region with an integrand of 1. Later on, you got to do the inertia, and that's a whole separate thing where you have to use an actual integrand. So we're basically doing 1 over dv. That's your interpretation of integrating over a volume over a solid. When you're actually trying to do your moment of inertia, you're going to be putting something there that's related to your axis, and a little chunk of that region is going to have a radius there and a weight, a little dv weight maybe, and your moment of inertia is going to be r squared times that, or something to that effect. Anyway, we'll have a little integrand there when we're trying to do the inertia. But for now, the whole issue is just setting up an integral where we can integrate over that region. So let's just do the volume. And we know it's supposed to be pi squared over 2 because he gave it to us. But us doing it will help us figure out how we're going to set up the integral to actually do the moment of inertia. So we're just going to do the volume. Ooh boy. Okay. So as I mentioned, I used to think you just always do z. I mean, I know you didn't always do z, but every calculus instructor I've ever had and every problem I've ever seen, it's set up to do v pretty easily. This one, not so much. It's doable, but you're not going to like this because this lower half, well, the lower half of the curve is given by sine inverse. Okay, so the original curve is, what is it? Z is equal to sine z. R is equal to sine z. Because the radius is, this is your R axis basically. Because when you do your three-dimensional picture, z there, x and y have specific directions. But now, when you do an R is any value there that can go around, so it can be an R that way, or R that way, or an R that way, or an R that way. So that xy plane, when you look at the side view like we are here, is like the R plane. R can be extending that way. It will rotate around, but that's our R axis. That distance right there will be how far it is from the origin, so that'll be R right there. And then we'll go straight up to Z. So it's a sideways sign where this is like x, and this is like your y, where this is y is equal to sine of x. But anyway, that's your graph that we're going to work with. When we do sine inverse, you get a value that's only from negative pi over 2 to pi over 2. So you can't get these z values by just doing sine inverse. Sine inverse will never give you values that are outside of this. So, once again, this one is easy. This lower half, because it's straightforward. I'm rearranging that. I'm doing sine inverse. So z is equal to sine inverse of r. Meaning that for every r that I use, like an r there, this will be z. That'll be equal to, which will be equal to sine inverse of r. I'm running small because this is not my main picture. And then I'm going to draw it bigger because I'm going to refer to it. Okay, so this is z is equal to sine inverse of r. Just solving that, taking the sine inverse of both sides, which means that when you have a random r on this r axis, that height of that z right there, is equal to sine inverse of whatever r value did. So r there, your z is going to be right there. R there, your z is going to be right there. So that's a relationship that goes from r, that distance, to the height. Okay, and that's going to help me do the other part of the parabola. Well, it's not a parabola, sorry. I don't know why I'm saying that. Okay, so I'm going to do it one way where I actually do find the two z's, and then I'll do it the other way where I just integrate with respect to r first, literally the first time I've ever done it. I don't think it's that bad, but it's just something that I would tell students in the STEM center, you just always do z. But no, like, apparently bachelor's going to be problems where you don't. Okay, that's what I want to do, this upper half here. Now for a particular r, that's my r right there, and this is my z that I want. So by the symmetry of it, it is symmetrical. So by the symmetry of it, that same r, I'm going to pretend it's the same r. It's a little bit, yeah, so let's say it's the same r. That's your sine inverse of r right there, that distance there. And translating it over there, that's this right here. That piece, that little corner of here, that little corner there is equivalent to the corner there with the same r there and there. So I'm using symmetry. So this distance here, right there, from there to there, is sine inverse of r. And the whole distance is pi, and that's sine inverse of r. And this is my z coordinate of this point that I'm trying to do for an r on the upper half of that curve. And that's going to be pi minus that. So my z here is pi minus sine inverse of r. So you're going to get creative to use your sine inverse, but it's not going to be as straightforward for the upper curve. Anyway, that's my two z's. And I guess I'll just replace them here. Now that I've worked it out. And then I'm just going to do that volume. Okay. Lower half is z is equal to sine inverse of r. Upper half is z is equal to pi minus sine inverse of r. And those are some ugly curves. And my theory is I believe he's intending you to do your integration with respect to r first, which is again unusual, but it looks like he's having you get creative and maybe making your problems more challenging because it's take home, everything's take home. I've done a lot of bachelor problems and I've really never seen this before. Anyway, I'm good to do it what I consider the usual way, which is to do z first. We are doing cylindrical, that it does have a Jacobian of r, and I'm going to be doing dz, dr, d theta. And I do want to mention that sometimes because that Jacobian, we're doing z first, and that's a constant, they pull it out and sometimes they move it next to the r. So sometimes I'll write this as dz, because you can disregard that r, or just bring it down. And then when you do your r, you need to include it. So sometimes they move it out there, but I'm just going to put it inside. And just make sure you treat it like a constant. Main thing is we set up our limits of integration. Okay, so in my plane, since I'm going to do with respect to z first, I'm going to pick a random r and theta. Bam, right there. That's my random r and theta, and I'm going to slice along the z. That point, let's say it's right there. This is the xy plane, but side view of it, and that random r and theta there that I placed there happens to be right there, and I'm going to slice along there. Bam, hitting my upper curve, slicing through. That's my slice there. Lower curve coming out the other end, a little bit off, but you get the idea. Okay, which means I got z is equal to pi minus sine inverse of r is my upper curve. Z is equal to just regular sine inverse of r is my lower curve. I'm going to go upper minus lower. Whew. Then I need to integrate over the footprint. So, and sometimes they call it a footprint. Sometimes they call it I think I like to call it a shadow, because the actual figure is just like barely balancing on that little tippy tip. But so, like if it's a footprint, it doesn't really have a footprint, but it's more of a shadow. Like you bring this down and you see what region it would make a shadow if the light were shining straight down. And it forms a circle with radius equal to that biggest, widest part, the hips of this thing. So let me draw that region. Let me draw that region because that's what I focus on now. This is my xy plane, or also my r plane. This is my z plane. And let me look at the bird's eye view of that region. It's just going to be a circle because that's your circle with a shadow. That's going to be a circle. What's the radius of it? That's what I need to know, really. Let me just draw a circle and I'll throw my radius afterwards. So it's just a regular circle. It'll be a very straightforward integration as long as I can find this radius. And that radius is based on the widest part of this base, which is here. And what's that length right there? Keep in mind what this graph is. It's r is equal to the sine of z. Here's my z. So that radius is 1. That's your regular sine. Just regular sine where it's going from 1 to negative 1 to 1 to negative 1. So it's 1. That's my shadow of that solid. And so that's what I got to integrate for the r part and the theta. And then fortunately it's straightforward. R goes from 0 to 1. Theta goes from 0 to 2 pi. And I believe I'm good. And if you recall, I was integrating just the integrand 1, but there's a Jacobian r. So let me see if it works out to what the answer he claims is. Pi squared over 2. Okay, doing z first. R is a constant. I'm going to be plugging in pi minus sine inverse of r and sine inverse of r into z. And I like to write it sometimes. Then we'll be taking that result and integrating with the r d theta. Alright, so I'm going to plug in for z. So it's going to be r times pi minus sine inverse of r minus another sine inverse of r. I'm going to skip a step here. It's going to be minus 2 sine inverse of r. Holy smokes. I don't know, man. By parts? I'm going to do a whole separate thing. Now I'm definitely sure he wanted to integrate with respect to r first. I'll do that afterwards. I'm gonna grind this out though. But make sure you understand the setup. Whether it works out nicely or not is irrelevant. If you can set it up, that's a good skill. That's a skill you need to be working on mainly. That kind of thing is, first of all, it's old stuff. Second of all, it shouldn't be that as bad as that. So definitely we're going to integrate with respect to r first. Let me see. I gotta do side work. I think I'm good with the setup. Take a picture of that if you need to, but I need side work to do one of my integrals. Specifically, well, the pi r is no big deal. It's my r sine inverse of r that is something I haven't seen in quite a while. So that piece is just a power rule. I'm integrating with respect to r next. That's r sine inverse of r. I'm going to do it on the side here. Let me use blue. And just so, I got to get this straight in my head. I'm just going to use x temporarily. It is a product thing, so you can't just do antiderivative. You need to do by parts whenever it's a product. And if you remember I late, the first thing is inverse trig function. So like that barely comes up. They oftentimes don't throw that at you during an exam, but that's inverse trig. Recall, this is what you set u to be. So I'm going to set u to be sine inverse of u. Sorry, sine inverse of x. My dv is therefore x dx. And then I got to do my du, which I don't know off the top of my head. So fast forward because I'm going to take 2 minutes to look this up. I guess I can do it. I'm going to do separate side work now. So this is, by the way, this is how you do inverse trig functions and find their derivative. You said y equals, take the sign of both sides, so you get a regular trig function. Do your derivative. It's implicit. It's going to be negative cosine of y times dy dx is equal to 1. It's going to be dy dx is equal to negative 1 over cosine of y. I'm going to do a triangle. Y, note that right here, y is an angle. Y is my angle because it's sine of y, so it's sine of an angle. That's x over 1, so it's going to be x over 1. That makes that x squared plus 1. And negative 1 over cosine. Negative 1 over, what's cosine? Cosine is that over that. Is that it, for real? Is it just negative square root of x squared plus 1? Let me check that. No. I have the right idea, but I messed up on my triangle. I set my sine to be x over 1. That's tangent, opposite over here. Okay, I gotta redo my triangle. I'm good up to there, though. My triangle is off, though. Okay, one more time. Sine of y. Y is my angle, which I'm going to draw a regular right triangle, make my y right there, and then sine is opposite over hypotenuse. Opposite over hypotenuse. That makes that 1 minus x squared square root of. I'm going to be doing negative, and cosine is that over 1, so it's done. Okay. That's my derivative of sine inverse. And that's what my du is. So I'm going back to my integration by parts. Yeah, this is crazy. dx, my v's antiderivative of that, 1/2 x squared. Alright, let's do this. So it's uv minus vd, so it's going to cancel. That's the whole trig substitution thing. I want to keep going with this. I think it's doable, but not in a practical, can I do this during an exam, and should I be doing this, or should I abandon this? This is abandoning it. I think I could work it out. I don't want to waste your time, because I definitely realize he wants us to do it the other way regardless. Alright. But that gives you an idea of how you would approach it. It's not, I'm not going to delete this video. I'm going to send it to you and let you watch me work this out, because it's a good lesson on just trying shit and seeing how it works, and that's not going well. And so I'm going to have to do my first time ever integrating a cylindrical, but with respect to R first. Okay, so that completely out because it was getting too bad, too ugly. Let's see what we got. Okay, the surface of this is R is equal to sine of z, was that it? R is equal to sine of z. Okay. I'm still going to integrate one, as my integrand just to find the volume and get his answer, hopefully. I do still have the Jacobian, so that's so my integrand is just R, the Jacobian itself. I'm going to do R with respect to R first. Then I don't think it matters, but I'll, right, as an alpha d, no, I want to do d theta first, I feel. Then dz. Okay, I'm sort of anticipating what I'm going to do. I'm still not 100% it's going to work, but let me set up my r first. And since I'm going to do it with respect to r, I got to find my r is the upper curve and then r is the lower curve. By picking a random theta and a random z. Our random z will be some arbitrary height here. Bam. Let me not put it in the center. Bam, right there. That's my arbitrary z. And an arbitrary theta. Theta being just angle that goes around. So it's just got to pick a direction. Bam. That's what I'm doing. So, bam, just coming out that way. Coming right at you. That's an arrow pointed at you. Okay. And you'll notice I put a little, that's not how I usually draw it. Let me redo this. It's cutting through, and it pops out like a bullet, an exit wound right there, and going that way. So I usually make my dot after. But the slice I make solid, just to be consistent with the way I've been doing it. I mean, it doesn't matter, it's just my personal way of drawing it. Okay, so just coming out of the football from the center, popping out, and going straight that way. And that's my r. My upper curve is the outer surface, the inner curve is that axis. So my outer r is just sine z. So I can tell it's going to be cleaner, and hopefully it's going to work out. And my r inner is going to be 0. From there to there, just out of the football, popping out of the surface. Okay, next I said I was going to do theta, so now I'm going to just integrate all those going around to the different thetas and getting this ring. And since it's the entire football all the way around, then it's going to go 0 to 2 pi. And then I want to do all the z's, starting from this tip of the football and doing all these rings, and going to the tippy top, which is at pi. So my z is going to go from 0 to pi. Anyway, that's a setup, but it's definitely going to work out better. Let me do it. Power rule in the R. By the way, I noticed, let me mention something. Now I noticed what he's been liking to do, which is that if he notices that this whole integran will not have theta involved, even after you plug in your limits of integration, therefore it'll be at a constant when you do respect to theta. He literally factors out the theta or something like that. So he starts separating it into separate integrals, which can make it easier, but you really have to interpret that I could do it for theta, but I can't do it for z because this integran here will have a z involved because of that limit of integration. It won't have a theta, so the theta I can split off, but not the z. And you have to really think about it before you start to do this fancy stuff that he's going to do. My recommendation is don't do it. Just do it layer by layer. So be conscious of that. I've seen in your notes that he's been doing that, and it's going to confuse you, I think. Because I have to really think it through when I can do that and when I can't. It's what variables are going to be in this after I do it, and anticipating that. And I can see I'm going to have r's out. Well, I'm going to have z. Once I do the r and I plug in for r, I have an expression with z. The theta, that means that with respect to theta, it would be a constant with respect to theta. So I can pull that entire constant out of my integral with theta, but I'm going to do that. There's no reason. I can just do it the usual way, and I'm just going to do it the usual way. Oh man, I just erased my work. So I'm going to get 1/2 sine squared z minus sine squared, or sorry, minus 0. Okay, so that's my first layer. Okay, next is with respect to theta, and that fancy thing that I just talked about, I said don't do, but it's still, you know, it comes out clean here because you have to remember this is with respect to theta, and this is just a constant as far as theta is concerned. There's no theta here. Z is a constant when we do this integration. So what's your antiderivative of a constant? It's that constant times your variable. And then we're going to plug in 2 pi and 0, and it's just going to go in here, and this constant will come down, which is why that thing of factoring it out works. But again, why bother? This is not much worse. So it's going to be 1/2 sine squared z, and I'm going to do 2 pi minus 0. So I just have a 2 pi factor. But I'm not done, because then I have, with respect to z, I'm going to go this way. And I'm going to factor, I should have factored out the constant anytime. You like to do it early. I don't really care when I do it. I'm going to factor out now the half and a 2 pi, and I'll just have sine squared z. Look at that. Tell me what you're going to do. You better recognize that, because it's going to come up a lot. It's a half angle formula. You can't do sine squared by itself. You have to use 1/2 minus. That's 2z. I might see this with a line through it, to be aware of that. And you should do something similar so you don't confuse it with a 2. Okay, constant. That's just z. It's going to be I did it mentally, but let me check my math. Derivative of that will be negative sine. Then I'll bring it 2 down. That's it. Okay. Plug in pi. 1/2 pi. Cosine of 2 pi, which is, whoa, that's not. Huh? Cosine of 2 pi is 1. Then I'm going to plug in a 0. Cosine of 0 is 1. Okay, so the fourths cancel. The fourths will cancel. That's times 0, by the way. That's 0. The fourth cancels. And that with half pi times this pi. Pi squared over 2. Yeah, that's the volume that he gave you, and that's how you're going to be integrating. Now, we need to do something else to the moment of inertia. We need to have a specific integrand, which we're going to discuss. But our setup for integrating over this football will be the same. It's just our integrand is going to be something that we have to set up to do moment of inertia. So our integrand will be different. Moment of inertia. What did I just say? Our integrand will be different when we try to do this, but our setup probably we're still going to go with this. It might be an integrand that's better to do another way, but there's no way it's going to be better. I'm going to think about that. I don't think it's going to be better the other way, but maybe if we throw in something, then that other way would have worked better than this. It is possible that with the correct integrand for the moment of inertia, the other way would be better than this way. I don't think it is, but it is a possibility we need to consider. Anyway, I'm going to save this and let you look at it, because you need to make sure you can set up an integral for this and understand the different ways and the different challenges before we are ready to tackle moment of inertia. And again, it's just going to be a different integrand that we'll have to deal with. But the setup is something you need to be getting good at.